In this video, we examine the integral form of Ampere's law, which relates a steady current to the magnetic field it produces. Let's consider the case of a straight wire carrying a steady current I. As is spelled out by the Biot-Savart law, the magnetic field B produced by this current is directly proportional to the current and inversely proportional to the distance away from the wire, here represented by S. The direction phi indicates that for a current going straight up, as is shown here, the magnetic field will circulate in a counterclockwise direction. We can represent the field using field lines, as shown in the figure. These field lines form circles centered around the wire that are perpendicular to the wire. For constant I, the magnitude of the magnetic field only depends on how far away the field point is from the wire. For the field points P1 and P2 shown here, the magnitude of B is the same, as they are the same distance away from the wire as each other. Now let's talk about the circulation of the magnetic field. When an electric current is moving in a line, a magnetic field is generated that appears to circulate around the current. This circulation is defined mathematically as the line integral of the magnetic field around a closed path. The circulation of B, the magnetic field, combines the strength and direction properties of the magnetic field around a directed closed loop in space into one scalar quantity. To find the circulation of the magnetic field for a long straight wire, we substitute the previously obtained definition of B for the long straight wire into the expression shown here. Now we have to choose a closed path over which to integrate. Although this is a formidable looking integral, we can use the fact that the magnitude of B is constant at a fixed distance away from the wire to help us. We choose a circular path that is a perpendicular distance S away from the wire. As long as the path is closed, we can follow it in either direction, but we choose to go counterclockwise, in the same direction as the magnetic field. When we carry out the integral, we find that all the terms are constant except dl, so we can move them outside the integral. When we integrate dl over the circular path, we get the perimeter of the circle, which is 2 pi s. When we cancel out the common terms in the numerator and the denominator, we're left with mu sub 0 times I, the current. This result has several interesting features. First, the circulation of the magnetic field is independent of the radius of the closed path we choose. This is due to the fact that as the radius s increases, the magnetic field actually decreases. In fact, it turns out that the circulation is also independent of the shape of the loop. What matters is that the path be closed and that the current enclosed by the path of integration be I. If instead of a single wire, let's say we had a bunch of straight wires, each wire carrying the same current I. Each wire that is enclosed by the path of integration contributes mu sub 0 times I to the circulation, while those outside the path contribute nothing, as shown here. The enclosed current is the net current that passes through any surface bounded by the path of integration. These ideas are summarized by Ampere's law, shown here. If the flow of charge is represented by a volume current density J, then the enclosed current is the surface integral of J over the cross-sectional area bounded by the path of integration, shown in red in the figure. Here is the integral version of Ampere's law again. This form of Ampere's law is valid for situations in which all the electric fields and currents are steady. We can think of it stating that the circulation of the magnetic field is proportional to the net current that passes through any surface that has the path of integration as its boundary, or that this path encloses the current that's under consideration. The surface that's bounded by the path doesn't need to be flat, but we usually assume it is because that is the smallest and simplest surface. Here are some examples of how Ampere's law can be applied to different current configurations. First, we have the conventional case, which we have already considered. The path of integration is a circular loop which surrounds the wire carrying current I, and the circulation of the magnetic field is proportional to I. If instead we enclose a wire carrying I but the loop is off-center, the result is the same, because the same current is enclosed as before. If the loop does not enclose the current carrying wire, the enclosed current is zero, and the circulation of B is accordingly also zero. In a situation where the wire passes up through the loop but then bends and goes back down, the net enclosed current is zero, and so is the circulation of B, the magnetic field. In the final case, the wire passes through the loop 3 times, and the net enclosed current is I, as shown here. In our study of electrostatics, 2 important concepts we used to help describe, analyze, and find electric fields are Coulomb's law and Gauss's law. In magnetostatics, the Biot-Savart law plays an analogous role to that of Coulomb's law, in that we can use it to determine the magnetic field associated with various current configurations. Ampere's law is the magnetostatics counterpart to Gauss's law. We have used Gauss's law to help us find electric fields, often by defining a closed surface in a given region, called a Gaussian surface, and calculating the area of this surface. This, along with determining the charge enclosed by the Gaussian surface, makes it possible for us to find the electric field passing through the surface. Similarly, we can use Ampere's law to determine a given magnetic field by defining a path of integration and the net current enclosed by this path. An example of how this is done makes this idea clearer. Let's use Ampere's law to find the magnetic field for a particular situation. Here we'd like to find it for a thick wire of radius A. This wire is carrying a current of I0 flowing upward. We want to find the magnetic field both inside and outside the wire. We'll begin by finding the magnetic field outside the wire. We'll choose a circular path of integration centered around the wire with a radius greater than that of the wire. This path of integration is also perpendicular to the wire. This means that the magnetic field is parallel to each infinitesimal line element in the path, and the magnetic field B the magnitude is constant everywhere along the path. Consequently, when we set up the line integral of the magnetic field along this path, we can move the magnitude outside the integral. This leaves dl alone to be integrated along the circular path, and the integral evaluates to be the perimeter of the circle, 2 pi s. The circulation of B in this instance equals the magnitude of B times 2 pi s. To use Ampere's equation, we need to know what the enclosed current is, and that happens to be I0. So the right side of Ampere's equation, mu 0 times I enclosed, in this case is equal to mu 0 times I0. Substituting into both sides of Ampere's law, we have the magnitude of the magnetic field, that is the magnitude of B, times 2 pi s is equal to mu 0 I0. We can use this expression to find the magnetic field outside the wire. We isolate the magnitude of B on one side of the equation and obtain an expression for it in terms of S. We have the magnitude of the magnetic field, and we know the direction of the magnetic field by the right-hand rule. It's in the phi hat direction. Here's the expression for the magnetic field outside the thick wire. The magnetic field is of the same form as the magnetic field outside a thin wire. So wire radius doesn't matter as long as we're outside the wire. We're going to have the same form. We can also use Ampere's law to find the magnetic field inside the wire. Here we set up a path. Here's the wire. And we set up a path over which to calculate the circulation of the magnetic field, which is, again, circular. It's perpendicular to the flow of current, and it's parallel to the magnetic field. As in the previous case, the magnitude of the magnetic field is constant all along the path of the integral, so we can take it outside the integral. And the integral equals the magnitude of B times 2 pi s. The enclosed current is part of I0. If we don't know the density function of the current in the wire, we will assume that the current is uniformly distributed throughout the wire. This means that the enclosed current is a fraction of I0 that is proportional to the ratio of the areas of the path of the line integral, marked in green in the wire, over the cross-sectional area of the wire. We substitute this expression for I enclosed into mu 0 I enclosed, and we use it in Ampere's law. We can then isolate the magnitude of the magnetic field on the left side of the equation, obtaining an expression that's a function of S. We know the direction of the magnetic field since the current is flowing upwards in the wire. By the right-hand rule, it means that the magnetic field is circulating in a clockwise direction. Now let's examine these results. The magnetic field B for the thick wire of radius A is a piecewise function. Inside the wire, B is equal to mu 0 I0 divided by 2 pi a squared, all times s in the phi hat direction. Outside the wire, the magnetic field B is equal to mu 0 I0 divided by 2 pi s in the phi hat direction. We can graph this function B as a function of S. To begin with, B is 0 at the center of the wire, which makes sense since no current is enclosed by the circulation loop there. We see that inside the wire, the magnetic field increases linearly as more of the wire is enclosed, and that's because more of the current is enclosed as a result. Once we get beyond the edge of the wire, all current is enclosed, but the magnetic field gets weaker as we move farther away from the wire. We also note that the magnetic field is continuous at the surface of the wire. Another example that we can consider is one where we have a magnetic field that is produced by a infinite uniform surface current that flows in the xy plane in the x direction. It's shown here. Okay. The surface current density K is equal to K in the x hat direction. So it flows, as I said before, over the infinite xy plane. Now let's consider the direction of B. Since the current I is flowing in the same direction as the surface current density, we use the right-hand rule to determine that above the sheet of current, the magnetic field is in the minus y hat direction, and below, the magnetic field is flowing in the y hat direction. There is no x hat or z hat component for the magnetic field. In order for us to calculate the circulation, we need to draw an Amperian loop. And we choose to put the Amperian loop into the YZ plane so that it is actually perpendicular to the flow of current. And we extend the Amperian loop equally above and below the surface, above and below the XY plane. The loop is of width L, and the height, all we need to know is it extends the same amount above and below the plane. At this point, that's all that's necessary for us to know. We're going to use Ampere's law now to determine what the magnetic field actually is. So in the Amperian loop, we're going to move in a counterclockwise direction. And the first segment we'll consider in the Amperian loop is the bottom one, which is marked in red, followed by the right side of the loop. This is the path that we're going to follow to calculate the circulation. That right side is marked in purple. The top, marked in orange, we follow it, moving to the left. And then we close out the loop on the left side in blue. And you'll notice that that in the loop that we're following the path, the red portion and the orange portion are in the same direction as the magnetic field below and above the XY plane, respectively. That's done deliberately. Now here's what we get. When we calculate the circulation, we take the magnetic field and we compute the dot product with the infinitesimal line integral. We have four portions. We have the bottom portion, we have the right portion, the top portion, and the left portion. We see that the way that we explain how we're moving, we use the magnetic field as it is below. That's the b sub y. We know that it's in the y direction below. And then we look, that's the only part that matters, because the movement, the infinitesimal line segment there, the only change that's occurring is in the y direction. So it's dotted with dy. And then to that we add the portion of the field that would be in the z direction, dotted with the path, the purple path. And then we have the portion of the field that would be in the minus y direction, dotted with the path for the orange part, followed by the portion of the path that's in the minus z direction, that's dotted with the path. And because we know already that the direction of the field is only in either the y direction, that would be for z less than 0, or in the minus y direction, that would be for z greater than 0. There is no component of B, the magnetic field, that flows in the z direction or in the minus z direction. So this means that those terms are going to be 0. And that means further that the purple segment of the integral, that integral and the blue one both are going to be equal to 0. So the only non-zero values that we're going to get here are going to be from the red integral and the orange integral, the top and the bottom parts. And so when we compute this, we get the integral, the red integral computes to be, we have by, and we're dotting that with dy, okay, and that's following that path, and that really just means that we're taking by, which is going to be constant along that line, and dy ends up integrating to just be the length of the path, which is this width L. Okay. And then the next integral is 0, evaluates to 0. The third integral also will evaluate to by. We have minus y hat dotted with minus y hat to be 1. The length of the path is L, And then the fourth integral, the blue one, is also going to evaluate to 0 because there is no z component for the magnetic field. And so the circulation of the magnetic field ends up being equal to 2 times by, it is the component of the magnetic field in the y direction, times the length of the Amperian loop, L, which is really the width of the Amperian loop that we use. So it turns out that the only dimension of the Amperian loop that really matters is L in this case, and that the height and the depth of the loop don't matter as long as we make it so that the loop is symmetric with respect to the xy plane, that it extends the same amount above and below. So we have the left-hand side of Ampere's law figured out. We have a value for it. We have to deal with the right-hand side now, which is mu 0 times I enclosed. So we have mu 0, and then to get the enclosed current, what we have to do is consider taking the surface current and saying how much crosses dl. Okay, and then we find out that we take the surface current density and we put that across dl, and that evaluates to mu 0 times k times L, and that gives us the value of the right-hand side of Ampere's law. So we have a simple expression for the left-hand side, a simple expression for the right-hand side, and we can substitute them both in and set them equal to each other. And when we do that, we find that by actually is just the magnitude of b, because above the sheet of current, the magnetic field only has a y component, but it's in the negative y direction. And below, it only has a y component as well. It's in the positive direction. They're of the same magnitude. So by is just the magnitude of the magnetic field. And so we can say that by is equal to the magnitude, and we substitute in the magnitude, and then we can get an expression from Ampere's law that is the magnitude of b. It's mu 0 times k, the surface current density, divided by 2. And this means that we have the magnitude and we have the direction. We already knew the direction of the magnetic field. The negative y direction for any point that is above the infinite plane, where we have the surface current flowing, and it's in the positive y direction below. So that means that we can get the entire value of b, both above and below this sheet of current, this infinite sheet of current. And you'll notice that there is nothing in this expression for the magnetic field that talks about how far away we are from the sheet of current. The value of the magnetic field is actually constant for z greater than 0, and it's constant for z less than 0. It's just that they're pointing in different directions depending on whether we're above or below. And that is because the sheet is infinite. So it doesn't really matter how far away you are from the sheet, you're going to always have the same magnetic field.